Thank you very much. It's a great pleasure to be at UCLA. It's my first time here, and these few days made me realize that not coming here earlier was a very grave mistake. So I hope to come back. And what I will try to tell you about today is some interesting new experimental results about exotic hadrons, also known as multi-quark hadrons, and about my own theoretical work that was done in collaboration with John Rosner. So, okay. All right, so we all know that quarks are fundamental building blocks of protons, neutrons, and all hadrons. And on first sight in QCD, all quarks are equal, but to paraphrase Orwell, heavy quarks are more equal than others. They're easier to deal with theoretically, and it's simpler to analyze the states which they involve. So I will discuss new states, including heavy quarks, a newly discovered tetraquark with two charm quarks, an anti-U and an anti-D, a theoretically discovered analog with bottom quarks, about which there is now theoretical consensus. It is stable under strong interactions. And another aspect of exotic states, so-called hadronic molecules, especially so-called pentaquarks discovered by LHCb, and there are 6 of them by the last count. And it's beginning to look like a new layer in a periodic table. So by now we have robust experimental evidence for multi-quark states, sometimes referred to as exotic hadrons with heavy quarks, specifically mesons, which are not just a quark and antiquark. For example, heavy quark, heavy antiquark, a light antiquark, a light quark, or 2 heavy quarks and 2 light antiquarks, and baryons, which contain as their valence quarks 5 quarks, 4 quarks, and an antiquark. And the 2 key questions that we should ask is which additional states to those, in addition to those that have been observed, we should expect, and how are quarks organized inside them? Are these tightly bound tetraquarks? Are these bound states of 2 diquarks, or maybe hadronic molecules? And to illustrate this and to establish what we mean by tightly bound tetraquark, a tightly bound tetraquark is an object inside which all the quarks are within one confinement volume, and each quark sees the colored charges of all other quarks. That's the definition. Whereas a hadronic molecule is a bound state, deuteron-like bound state of 2 color singlets, quarks in one hadron coupled to each other, and quarks in the other hadron coupled to each other as well, but quarks in one hadron do not talk directly via color forces to quarks in the other hadron. And in September 2021, the latest striking experimental discovery was done by LHCb. They observed a narrow, very narrow, doubly charmed tetraquark decaying into 2 D mesons, not a D and an anti-D, 2 D mesons, and a charged pion. So the quark content is completely unambiguous. This thing is very, very narrow. It's a tiny little bit below threshold. You can see the threshold is here, and this is just a bit below. And depending on how you analyze it, you can analyze it with Bright-Wigner, but that's usually considered not a very good idea when you're close to threshold. And there is something called pole mass and pole width. If you do it like that, in any case, the distance from the threshold is a few hundred keV. And the width, depending how you define it, it's either 48 keV or 400 keV, much less than 1 MeV. And this is just for fun, a compilation which was done by the experimentalists of the various theoretical predictions for the mass of this object. And by pure accident, ours is in red. Okay. I want to make a small digression. This object is a tetraquark which contains 2 charm quarks. But there is another object which contains a charm quark and a charm antiquark, and a light quark and a light antiquark, which has been known for 20 years. It's very well studied, called X3872. This, by the way, the discovery of that particle is the most cited paper from the Bell collaboration, more than anything they have done in Kobayashi-Masukawa angles. And so the reason I'm showing this paper is that, to my knowledge, this is the first time people were able to observe such an object in heavy ion collisions. And the cross-section in heavy ion collisions is most likely much larger. And so it's important that they were able to overcome the background and see the signal. And we all hope that the heavy ion experiments will be able to observe other states which are very difficult to see in experiments like LHCb because they have a small cross-section. So going back to heavy quarks are more equal than others, the reason they are more equal is they're almost static. They have little kinetic energy for uncertainty momentum of a few hundred MeV. They have small spin-dependent interaction, and these 2 qualities have been the key to accurate prediction of many different states. So we decided to apply them to some more exotic states. So I should state in the beginning, we are here at the QCD conference, QCD at 50. But this calculation was done within so-called quark model, which is an effective theory which was arrived at by trial and error of many smart people, people like Dalitz, Lipkin, Rosner, Isgur. But it would be nice, as we discussed in yesterday's lecture of Ian, it would be nice to derive the quark model in a controlled fashion, because sometimes it works exceedingly well and sometimes it doesn't work at all. But in this case, it seems to work well. So the approach is that you identify the effective degrees of freedom and their interactions, extract the model parameters from experiment, and then use them to make predictions. And the 2 problems to which we applied this toolbox were, first of all, a doublet charm baryon, which, when we wrote the paper in 2014, had not been yet observed, but it's not exotic in any way. It's as benign from QCD point of view as the proton. It was just a question of having enough cross-section and sensitive enough detectors. So it was an ideal test ground. And later on, two doubly charmed tetraquarks, where the two charmed quarks are coupled to a color antitriplet, and the two light antiquarks are coupled to a light color triplet. And so in 2014, we predicted the mass of this object as 3,627 MeV, and 3 years later, it had been measured at 3,622 MeV. And when we saw that, we realized that probably in this case, the quark model works rather well, so we decided to apply it immediately to the tetraquarks. And another thing which we saw was that the lifetime, the measured lifetime, is here in red, and this is our prediction for the lifetime and some other predictions. So everything seems to work more or less okay. Now,
could you just say roughly, quickly, what the input into that calculation is?
that's this transparency, precisely.
Mark, why does it come out at spin 3/2 and not half?
No, it comes spin 1/2. Who said spin 3/2?
I saw on the slide, the first slide.
No. Excuse me. What am I doing?
I just saw M at J equals 3/2.
Yeah,
I see.
but not the one that was measured. The one in the red box is spin 1/2. Okay? All right, so what are the ingredients of this dish? The constituent mass of the two charmed quarks, the constituent mass of the light quark, the interaction strength between charm and light quarks, and then in red you have two things that because of which we got stuck for a very long time, because there is no other system in nature from which you can extract this. So we have been talking about this problem for a long time and, didn't know what to do. So finally, we made a conjecture, which at the time we had no idea whether it's going to work or not. If you look in one gluon approximation, then one gluon exchange, then the interaction between a quark and antiquark in color singlet is exactly twice the interaction between two quarks in a color antitriplet. It's just the Casimir of the representation. So for lack of anything better, we postulated that this is going to be true also for these bound states. And I think we now understand why it's true, but then it was not clear. And from there, it's downhill because you can extract this from charmonium.
So there is a prediction for nearby 3 halves.
Yes, there is.
Has it been seen?
Not yet. Not yet. But it's there, and one nice thing is that it can also be looked at on the lattice. So we can compare. I don't think it has been done yet. All right, so there are effective masses. That's what you ask. Okay. Now, so this is the observation, and when you do that and extract the interaction of two charm quarks from charmonium, take factor of 1/2, you get about 130 MeV binding energy. And you have everything you need. And this is how you arrive at the prediction for the mass. So the quark masses are here. The binding is here. This is the hyperfine binding, which is spin dependent. And this is the hyperfine binding between the light and charm, and that's the number. Okay, so what you see, the most important The most important number here is this very large interaction energy, 130 MeV between the two charm quarks, and I will explain in a moment where it comes from. But once we saw that, the reaction was, okay, so maybe we should go back to the old idea of Bob Jaffe, where you have 6 quarks, 2 U's, 2 D's, and 2 S quarks, and he conjectured that such a state is bound, and people have looked for it for a long time and didn't find it. Probably it's not bound. But with this extra binding energy, we thought, okay, maybe we should have a look at this. And indeed, the mass of such an object with 2 charm quarks is below the 2 lambda c threshold. But unfortunately, it's above the threshold of a baryon with 2 charm quarks and an ordinary nucleon. So that idea is not useful, but it's an ugly duckling. Because once you realize that this is what's going on, the same theoretical toolbox that led to the accurate prediction for the doubly charm baryon mass now predicts a stable, deeply bound tetraquark with 2 B quarks and 2 anti-U and an anti-D. In our calculation, about 200 MeV below the 2 meson threshold. In other calculations, 100 MeV. But by now, there are 3 different analytical calculations, one ours, one with heavy quark symmetry, one in large N, and several lattice calculations. And everyone agrees that this object is deeply bound. So why is it deeply bound? That's the most interesting question. That was our paper, where we predicted also the cousins with double charm and bottom charm. So let's have a look at this object. It's actually very similar to a baryon, but with 2 charm quarks or 2 bottom quarks. You have 2 charm quarks, which form a diquark. Now, because the quark is a color triplet, these 2 charm quarks must form a color anti-triplet, and therefore they're antisymmetric in color. But since they have the same flavor, they must be symmetric in spin by Fermi statistics, and therefore this diquark must have spin 1. Now, if you go to the tetraquark, it's the same story again, no difference. But these 2 guys then form 2 color anti-triplet, bind into a color triplet, and the forces between light quarks are very much spin dependent. So a diquark with spin 0, isospin 0, is about 200 MeV lighter than the diquark with spin 1 and isospin 1. And these 2 diquarks bind to each other by color forces in an S wave, so you immediately have a very robust prediction that this object must have spin 1 and positive parity. If it's measured experimentally and the spin and parity are different from what I just told you, then it kills this whole approach.
Did you take into account the weakening due to asymptotic freedom when you look at BB? I mean,
Yeah, well, in principle, it's taken into account through experimental data from bothomonium. Because you take the numbers from bothomonium. So it takes care of itself, so to speak.
I thought you were doing 1 gluon exchange.
No. In 1 gluon exchange is the quote-unquote inspiration. And then you postulate this holds for a bound state as well. Okay? So now the fact that such an object with 2, excuse me, what am I doing? The fact that such an object with 2 heavy quarks and 2 light antiquarks is bound, it's easy to see it must be true for sufficiently heavy quarks, because the binding energy scales like alpha s squared times the mass of the heavy quarks. For sufficiently heavy quark, it must be bound. But no one knew if bottom is heavy enough. And what the LHCb experiment did for us, it calibrated the calculation. So here you have the numbers, and here for bottom, you have this huge number, 280 MeV binding energy. And where does this come from? And it's actually amusing. So people have known for, I think, almost forever, very quickly after QCD was discovered, that the heavy quark potential can be approximated by a Coulomb term and a linear term. And when you have two heavy quarks, they stabilize at a very small distance, about 1/5 of a Fermi. Now, 1/5 of a Fermi, 1/1/5 of a Fermi is 1 GeV. So when you multiply 1 GeV by alpha s, you get a big binding energy. Now, this shows that sometimes when you hear in popular literature that forces between quarks become weak at small distances, this is not true. What becomes small is the coupling. But if you have two heavy quarks and they're close to each other, then there can be huge forces, even though they're quite close to one another. Now, why is this thing bound? Why it cannot decay into two mesons? This interaction is between two B quarks. So when you dissociate it into two B mesons, you lose this attraction between one B in one meson and the other B in the other meson. And so you lose almost 300 MeV. That's why you find it well below threshold. So it's stable against strong decay. And of course, it decays weakly, as B quark doesn't care where it is. But with a lifetime, which is 10 orders of magnitude longer than a typical strong interaction scale. So from the point of view of strong interactions, it's a stable state. Now, this plot shows our estimate of the distance from the threshold of two mesons for states with two B quarks, B and a C, and two Cs. We estimated that it was 7 MeV above threshold. It turned out to be about half an MeV below threshold. But the pattern is clear, and therefore, we probably should expect that this state, BC, which is easier to make than BB, is below threshold and is also stable. And LHCb, people in LHCb are working very hard on inventing a search strategy, because it's not easy. All right, you produce it the same way you produce the doubly bottom or doubly charmed baryon. And the only difference is in the hadronization stage. You make a diquark with two charmed quarks or two bottom quarks, and then it dresses up either with one quark, in which case you have a baryon, or with a light diquark, in which case you have a tetraquark. Now, since LHCb has observed this CCU, you can make a rough estimate that the cross-section for making doubly bottom baryon is roughly that cross-section multiplied by the probability of making a B-B pair rather than a C-C pair. Very rough, and it's borderline, probably not possible with the current luminosity, but with high lumi, probably they can do it. Okay, so there are all sorts of clever tricks that people have invented. I don't have time to discuss them, but maybe they will be helpful in extracting this thing from data. You can look it up in my transparencies. A crude estimate of the lifetime is a typical weak interaction decay lifetime, slightly more than 400 femtoseconds. And many decay channels, which in fact is a problem because each channel has a small probability, and real-world experiments need to focus on particular channels. So it's very tricky. All right, so to summarize, we have a stable, deeply bound BB U-bar D-bar tetraquark with spin 1 positive parity, deeply below 2 meson threshold, the first manifestly exotic stable hadron. It has a bunch of decay modes that are easy to predict. The cousins with double charm, the cousin with double charm has been observed tiny little bit below threshold. And the cousin with one bottom and one charm is very likely order of 10 MeV below threshold. OK, so this is just transparency prepared by LHCb showing 59 new hadrons discovered in LHC, many of them exotic, many of them by LHCb. OK. Now I want to shift gears and talk about a very different kind of multi-quark states. These are mesons that share some characteristics. One is that they are very close to 2 meson threshold. The other is that they decay into a quarkonium, J psi or upsilon, and a pion or 2 pions. And the third quality which they share is that they're exceedingly narrow, ridiculously narrow. And what do I mean by that? Ridiculously narrow means, for example, this state, which has been discovered by Bell, has 1 GeV of energy available for its decay into upsilon and pi. But its width is 20 MeV. This is crazy. I mean, there must be some efficient mechanism impeding the decay. Otherwise, it doesn't make any sense. So I will try to convince you that the fact that these are hadronic molecules is a natural mechanism for explaining why it takes so long for these things to decay. And what is also interesting, sometimes we learn something interesting when we don't observe something. So we see experimentally, we see states which are pseudoscalar in a vector, here and here, 2 vectors. But we don't see, neither in charm nor in bottom, we do not see 2 pseudoscalars. Again, it will turn out this is very natural in the hadronic molecule picture. So think about these hadronic molecules as heavy deuterons, where you replace one of the quarks by a heavy quark, one of the light quarks by a heavy quark in each of the 2 hadrons. And I want to show you some additional striking data. So this is this guy, which has a total width of 21 MeV. It can decay either to upsilon and a pion with 1 GeV of available energy, or it can decay into a B bar and a B star with 1 or 2 MeV. Now, you would expect that the decay, which has 1 GeV of phase space available, is dominant. But in reality, it's just the opposite. This state decays 86% of the time to this B bar, B star with a tiny little phase space, and only 0.5% to the state where there is huge energy. Now, what's going on? What is going on is that Fermi taught us that probability of a process is the product of matrix element times phase space. Matrix element is just the overlap of the wave functions. So obviously, the wave function of this object is very, very close, dramatically closer to the wave function of this object than to this object. And why is it so? Because the binding energy is very small. When you have a small binding energy, the radius of a state scales like 1 over the square root of the binding energy. So these are big objects. Here you have a B meson. Here you have a B bar. Here you have a B star. And they are far from each other. In order to hadronize into upsilon and a pion, the two B quarks need to get close together. But the probability of that is tiny. It's like the probability of electron going through the nucleus of an atom. It's small. It's just geometric factor, essentially. OK? And so we have 4 pieces of experimental evidence in support of the molecular interpretation. First of all, masses are near thresholds, which you expect with weak binding. The spin and parity of these objects are inherited from the constituents. This is what you expect in S wave, and you expect an S wave when you have weak binding. They are narrow despite very large phase space. The branching fraction to fall apart mode is much bigger than the branching fraction to quarkonium. And I mentioned in the beginning that you do not see these guys. Okay? Now, these hadronic molecules bind by exchanging light hadrons. What is the lightest hadron? It's the pion. But 2 pseudoscalars cannot exchange a pion. It's forbidden by spin and parity conservation. So these guys lack the essential mechanism. These 2 pseudoscalars here, they lack the essential mechanism, which apparently is essential for binding. So everything is consistent. Now the next step, excuse me. OK, so the next step is to realize that this binding mechanism can apply to any two heavy hadrons which couple to isospin. They don't have to be 2 mesons. They can be a baryon and a meson, 2 baryons, etc. And it's very easy to draw a list of such states. We did that in 2015. And the lightest interesting state is a molecule consisting of a sigma C and D bar star. And you expect it slightly below threshold and its obvious qualities. And we were very lucky because 2 weeks or 3 weeks after we published our paper, LHCb announced the discovery of exactly such a state.
Mark,
Yes?
I just remember that in the Deuteron,
In?
Deuteron,
Yes?
it's very hard to use the pion model to actually predict whether it's bound or slightly unbound. You have to kind of include the sigma-mizer or something.
No. Pion is not enough to provide binding. But without pion, you don't have binding. Yes. That's the statement. OK? So it's an essential ingredient. It's not sufficient. It's a necessary but not a sufficient condition.
So your prediction is that this could be a bound state, but you cannot make a definite statement.
Yeah.
Yeah. Okay.
So what they saw is a beautiful plot of a bright Wigner, so-called Argand plot, just about 12 MeV below threshold. You see the amplitude in the complex plane is rotating counterclockwise. And what happened, this was in 2015, and a couple of years later, they refined their precision, and now it's really stunning, because what we see now is there are 3 states. One at the threshold of sigma C, just below the threshold of sigma C and D bar, and 2 states just below the threshold of sigma C and D bar star. Now, why do you expect 2 states in one case and just 1 state in the other? If you have a hadronic molecule which is a bound state of a spin 1/2 baryon and a spin 0 pseudoscalar, there is only one possible S-wave state. But if you have an S-wave bound state of spin 1/2 baryon and spin 1 meson, then you can form either spin 1/2 or spin 3/2, and they're split by a few MeV. And this is what seems to be going on. And now I want to abstract from what we heard so far and discuss a certain regularity that seems to take place in the real world, which is that the only states that we think, we are convinced, form tightly bound tetraquarks are states which contain 2 heavy quarks and 2 light antiquarks. All the known multi-quark states with a heavy quark and a heavy antiquark are hadronic molecules. Now, it looks like a contradiction at first, because I just told you that the interaction between a heavy quark and a heavy antiquark is twice as strong as the interaction between a quark and a quark. So why can't you form a tightly bound state? And the answer is kind of trivial once you think about it. It is true that quark-antiquark attract twice as strongly, but they do that only if you put them in a color singlet. If you put them in a color singlet, they don't talk to the other guys. They hadronize as quarkonium. End of story. So the only way to construct a multi-quark state is if you keep them apart. One sits in one hadron and the other sits in another hadron, and they exchange light hadrons. You can never utilize this strong attraction to make a multi-quark state. Whereas with 2 heavy quarks, you have no choice, because 2 heavy quarks give you a color anti-triplet, which cannot exist as an isolated state. It must bind to something else. So that's what's going on. Okay. Now, just to mention briefly, LHCb has now seen completely analogous states with strange quark instead of one of the light quarks. These objects decay into J psi lambda instead of J psi proton. And we believe there are molecules containing, making the same mistake again and again.
These are not near threshold.
They are near threshold. They are near threshold of sigma c and d bar star, very near threshold. And in addition, we expect 3 more states near the threshold of sigma c prime and d bar star and d bar.
You're talking about the ones that were in the news just a month ago?
No. In the news where...
I was talking about those.
No, but okay. The ones that were in the news are most likely yet another hadronic molecule, or maybe...
Those are pretty far above.
Yeah, but those I will not talk about today. Okay, so now I want to mention briefly something where the 3-string vertex enters. This is something we have been discussing in several talks, and it's amusing that you can put it to work to make a very simple calculation and obtain a mass which agrees with the data very, very well. So LHCb again has discovered an object which is a narrow resonance decaying into D plus and K minus, and the quark content is obviously CS, not CS bar, U bar, D bar. So this is just like the ones that we were discussing before, 2 charm, 2 bottom, except that you replace one of the heavy quarks by a medium heavy strange quark. Now, this doubly charmed tetraquark was found just below the 2-meson threshold, and therefore you expect this one significantly above the threshold, because mass of an object comes from potential energy plus kinetic energy. When you make an object lighter, its kinetic energy is higher for a given momentum. So okay, so we sat down and calculated, and using the string junction picture. So this is how the string behaves in a meson. This is how it behaves in a baryon. This is how it behaves in a tetraquark. And just from studying baryons, you can infer that the vertex contributes about 165 MeV to the mass. And so you plug it in, and you obtain, I'm going to skip this, we don't have time.
In the tetraquark, the heavy quarks were in the Coulombic regime, not in the string regime.
Exactly, exactly. But here,
Oh, they're lighter, so they're in the...
precisely. So that's precisely the point. Here, one of the heavy quarks was replaced by S. And this is why the stringy regime becomes relevant again. Okay? And so, you know, you obtain, I mean, it's a trivial calculation, 2863 MeV. But you know, you can do it in 5 minutes. Almost too good to... Okay, and of course there is a prediction, and that's the real test for bottom. Bottom strange should be accessible, and hopefully will be seen, and then we will know. All right, so I should speed up. Another experimental result, which is very interesting, is a resonance discovered by LHCb, which decays into 2 J psis. So its quark content is 2 Cs and 2 anti-Cs. And by using similar technology to the one that I described here, we inferred that probably what this is an excited 2s state, 0 plus plus 2s. And we predicted this at 6.871 GeV. It was measured at 6.9 GeV. There are some other predictions that I don't have time to discuss, but with more data, and perhaps with the resonance decaying into 2 upsilons, or 1 upsilon and 1 J psi, we'll be able to test these ideas. So I think I should summarize and leave some time for questions. So first of all, a narrow doubly charmed tetraquark was discovered by LHCb with properties closely matching those that have been predicted. Doubly charmed baryon was found exactly where predicted, and it's just a question of luminosity to see the other doubly heavy baryons. There is nothing unusual about them. Theorists, using different approaches from lattice to analytical calculations, are completely convinced that the doubly bottom tetraquark is bound under strong interactions. At the moment, the most likely candidate to discover it experimentally is LHCb, but perhaps someone will invent a clever way to do it in heavy ions. We have a large number of hadronic molecules already discovered, and many more should be seen in future. We have seen at least one example which is suggestive of 2 string junctions playing a role in generating the mass of an observed tetraquark. And I think it's fair to say that there is exciting new spectroscopy awaiting discovery. And when I talk to my colleagues who work in BSM physics or string theory, they tell me that I should feel lucky because typically I can write a paper and in a year or two there is either an experimental confirmation or refutation, which is very rare now in our field. So I feel I'm very lucky. So thank you very much.
Thank you for the very nice talk. Just a question. In one case, the CC U bar D bar, you didn't use any junction. In that case, you did.
That
and
was,
also
that was Zohar's question, exactly.
Yeah. Okay.
The point is the following.
Yeah.
When you have two charm quarks,
Then
they stabilize at a very small distance where the potential is dominantly Coulombic. You don't form a string.
okay, that's it.
But when you have charm and strangeness, you enter,
Yeah. Then you have a large separation, and then you see
Exactly.
the string.
okay?
But then I also remember in some of your papers you were talking about baryonic constituent mass versus mesonic constituent mass.
Absolutely. Thank you for the question. Just a question. So, what people found in the heyday of quark model is that they could reproduce the masses of all the known baryons of all the ground state, at least, baryons, and some excited states, and all the known ground state mesons and some excited states this way, but with a 65 MeV difference between quarks used for baryons and quarks used for mesons. So another way to put 55, excuse me, yes. Zohar is right as usual. So an obvious interpretation is that you either keep the mass as a constituent mass of the quarks in the baryons, or you put it in the vertex. That's what's going on, okay? And it comes up to the same, okay?
Yeah, I was just wondering why with 6 quarks, why didn't you take 4 charm and 2 light or anti-light? You put 2 charm and an anti-triplet, the other 2 charm and an anti-triplet.
Probably it's going to work, but you mean it would be a baryon-like configuration?
Yeah, exactly.
I think it's probably going to work, but since, as I mentioned, I like to see the things that I write papers about measured.
But
Yes.
heavy ions have charm quarks up the wazoo. It would probably be easier to look at I think Barbara would agree with me, than PP, right? Because in PP, the chance of getting 4 charm.
Well, absolutely. That's why I showed this transparency from CMS, where they were able to overcome the huge background to identify X3872. But if you look at in some detail at what needs to happen in order for a 6-quark state like that to be formed, you're exploring a very tiny piece of phase space. So maybe nobody will be happier than me if they see it, and I think it's likely that it is bound, but
Never underestimate heavy ion experimental.
I don't. Yes, Barbara?
So I just had a very short comment to make, which is that the collective flow that I showed you in nucleus-nucleus collisions also is there in p-nucleus, and that gives actually another tool for looking at the quark content. Some of the exotics, maybe we're not sure how many quarks are in there. For example, the F0980 was shown to flow as a 2-quark object rather than a 4-quark object. So that's perhaps another tool that can be used.
And I should mention femtoscopy, which is a very beautiful tool developed by people in the heavy ion community, which makes it possible for them to extract the potential between two hadrons looking at their correlations. And once you have the potential, you can sit down and see if a molecule is likely to be formed or not. So this is nice.
So for your stable tetraquark, are there predictions for the branching ratios, in particular the branching ratios involving J-psi, which are presumably easier to trigger?
Tiny, 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 because what you need, I mean, 1 J-psi is no big deal, but 2 J-psis, I mean, there is a mode with 2 J-psis.
Well, one would be enough to trigger, though, right?
Yeah, right. So we have not worked out them in detail, but I would expect, where is it? No, that's... Yeah. So the modes with J-psi are here. We have not done a calculation, not out of laziness, but rather because to do a bona fide calculation, you need to know a little bit more about the wave function and the overlap and so on. So maybe people can do it on the lattice, a 3-point function, I don't know.
So there are no detailed predictions for branching
No, but
ratios.
there is another mode which is very interesting, which is this, which is W exchange into D0 or B minus. That's very cute, just two body. Maybe one can calculate it using standard, weak interaction toolbox.
Yeah, I vaguely remember there was a paper based on a lattice calculation of a dibarion made of 6B quarks. They claimed it's very strongly bound.
I know this paper, and I think it's probably incorrect.
So it doesn't agree with your model.
No, it's not just that it doesn't agree with me. There is a general properties of potential theory are such that if you have, for example, two Bs and two anti-Bs, it's easier to analyze, okay? Most likely it will never be below 2 eta B, 2 pseudoscalars, because in eta B you maximize the attraction. So the general belief among experts, people who have spent their lives playing with potentials, is that it will not happen. You need light quarks in addition to heavy quarks to have something stable. You need a big mass ratio between the constituents in order to form a bound state.
They just did the lattice calculation.
I understand. I am not in a position to to tell you where in the lattice calculation they might have done something incorrectly. But I don't believe the result.
Okay.
Thank you.